In our last video, we discussed the classical description of light, namely that light behaves as a wave, experiences interference effects just like all waves. But we also mentioned that there were certain circumstances under which that classical theory doesn't seem to work. In this video, we'll take a look at those circumstances under which classical wave-like behavior is not observed, which necessarily resulted in the development of new theories about light and, as we'll see later on, about matter itself. First, we look at the specifics associated with these failures of classical theory. The first one we'll discuss is blackbody radiation. You may have remembered discussing this in general chemistry, but this is an effect associated with what we call an ideal emitter, and that is an object that emits evenly through the electromagnetic spectrum. And what we observe when we look at that is that there's a temperature dependence of the emission of light from a black body, and there's also a frequency dependence of this emission of light from the black body. Neither of which can, as we'll see, be explained by the classical theory of wave-like behavior. The other phenomenon that we'll be examining is the photoelectric effect. This is the effect that occurs when electrons are ejected from a metal surface after being struck by light. Again, we'll find that the behavior of the electrons and the frequency dependence of the energy of these electrons cannot be explained by simple classical theory and description of light itself. So we start with blackbody emission. Now again, we talk about this as being from an ideal emitter. If you read the sections in your textbook, you'll find a little bit more information about this. Here we're just going to look at the basics behind the phenomena of blackbody radiation. If we look at this particular graph here, which is spectral density on the vertical axis, which is very simply the energy of light emitted per unit volume, plotted versus the frequency on the horizontal axis. This is the frequency of the radiation, which again has the same definition of frequency of a wave that we talked about in our last video. Now, when we look at the effects here on this graph, we'll notice that as temperature increases, the frequency distribution tends to shift to higher frequencies. We can see this shift here as we go from 3,000 to 4,000 to 5,000, 6,000 Kelvin. We'll see that the general shape, the general envelope of the emission shifts to higher frequencies, which means it shifts to the right here on this graph as the temperature goes up. Not only that, we'll see that as the temperature increases, more energy is emitted, and that probably should make sense to you. Temperature obviously is related to energy. Higher temperature corresponds to higher energy, so we see more emission, and that is actually indicated by these graphs by the fact that the peaks get bigger. You notice that the maximum at 6,000 here is much higher than that at 3,000. And more generally, or actually more specifically, the area under the curves emitted. We'll learn that this area under the curve is an indication of the total energy per unit volume emitted at a given temperature. So because we see this increase in the maximum and the increase in the area under the curve, that's an indication that there's more energy emitted at the higher temperatures than certainly at the lower temperatures. Example of blackbody radiation and the kind of shifts that we see here might be something that you're familiar with. If you just, for example, take an iron poker and heat it in a fire, you notice as it gets hot and starts to glow, we'll see that it starts by glowing red, then continues to get hotter, it will glow orange, and on to yellow. And finally it will glow white hot, which white you may remember is a combination of all colors. And at this point the iron will melt at temperatures higher than this. So we won't see a shift in color beyond the white in the iron itself. But again, noting the electromagnetic spectrum, red light is lower frequency than orange light, which is lower frequency than yellow light. So again, this shows that as you increase the temperature, the shift from red to orange to yellow is indicative of an increase in frequency, which again is what we see here in this plot on the right hand side of the slide. We can also talk about this with regard to stars, and if we look at a few stars in the sky and constellations, and we may point this out in class, but for example, a red star, a red giant, is a cool star, and blue stars are hotter. And again, red is a lower frequency than blue, and this is again indicative of the temperature and the energy. An example of a red star might be the star Betelgeuse, which is in the constellation Orion, which is most apparent in the fall and winter months here in the northern hemisphere, and the blue star Sirius, which actually is the brightest star that appears in the northern hemisphere in the sky, also most apparent in the fall and winter months. So again, the blue being a higher frequency also indicates that we have a hotter star in that circumstance. So this is the basic observation, blackbody radiation. This increase in frequency that occurs as the temperature increases, which seems to indicate somehow the frequency is related to energy, which is a very non-classical result, and we'll talk about that in more detail in a few minutes. Now this graph just simply shows, rather than spectral density versus frequency, we have a graph that shows spectral density versus wavelength, and again what we'll note here is that when we look at this at the two temperatures here, plot at 4,000 and 3,000 Kelvin, that as the temperature goes up, the wavelength goes down. Now, we just graphed this to show that it's the opposite effect of frequency. As the temperature goes up, frequency goes up, but wavelength and frequency being inversely proportional, we'll find that as temperature goes up, the wavelength goes down. So we see on this graph a shift to the left on these curves. The other thing that I want to point out here is lambda max. We'll be talking about the importance of this on the next slide. But lambda max simply corresponds to the wavelength that is the maximum in the spectral density. So that when you see that lambda max, that just simply means the wavelength there. And again, what we'll see here, as we would expect, is that as the temperature increases, lambda max shifts to lower wavelengths. As we go from 3,000 to 4,000 Kelvin, we see that shift to the lower wavelengths here. Alright, so when blackbody radiation was first studied, scientists took the empirical data and determined specific equations associated with that before developing a theory about why this might be the case. The first one is Wien's displacement law, which simply relates the lambda max to the temperature is equal to a constant, and the constant's listed here on the slide. The important thing again is to note is that lambda max and temperature, because the product of the two must always be the same value, that they're inversely proportional, meaning that as temperature goes up, lambda max goes down, and vice versa, since their product must always be the same. And again, that's what we observed on the graph in the previous slide, but here is a specific mathematical relationship that would allow us to calculate these things. And for example, one thing we can do is, if we observe a star, the spectrum of the star, and determine the lambda max from that spectrum, that would allow us, using this equation, to calculate the surface temperature of the star, which you will find as a calculation accompanying the worksheet for this video. The other is the Stefan-Boltzmann law, which relates to total energy density, E over V, which we talked about that, and this would be essentially the area under the curve that we discussed earlier, as being equal to a constant A. In this particular plot, A here represents a constant times temperature raised to the fourth power. So it is proportional to temperature to the fourth power. So again, the energy density increases, the temperature increases, but it's well beyond a linear relationship. It goes as the fourth power, which means if you increase the temperature by a factor of 2, the energy density goes up by a factor of 2 to the fourth, which is 16. So an increase in temperature by a factor of 2. And again, the temperature scale that we're dealing with here is kelvins. Keep that in mind. So if we were to increase the temperature from, say, 300 kelvins to 600 kelvins, the total energy density would increase by a factor of 16. Alright, so those are the observations from the empirical data associated with blackbody radiation. So if we apply the classical description of light behaving as a wave, as scientists did in the 19th century, we'll find that those classical descriptions just will not yield the simple results that we observe. The increase in frequency as temperature increases. We cannot, with classical results, reproduce the graphs, the plots of the data that we looked at on the earlier slides. We'll find that the classical description works reasonably well when the wavelengths are high or the frequencies are low, but we'll find that in fact, as we continue to, if we increase the frequency to higher wavelengths, rather than the curve reaching a maximum, it just continues to get higher and higher and higher, so that the energy density will approach infinity as the frequency gets higher. There is no maximum in these curves. So the classical description of light just simply will not work in explaining the maximum that we saw. And so here we see a graph that shows this increase in frequency. Again, the energy density is plotted on the left side of the vertical axis here. So it just goes up and up and up. At no point do we see it ever reach a maximum and come down as we observe in with the empirical data. So the classical behavior just will not work. And so what that means is that we need a new theory to explain blackbody phenomena. So this is where Max Planck comes into play. And right at the turn of the century, in 1900, Planck decided to try to come up with a theory that would explain blackbody radiation. So he very simply started with the data and said, okay, let me see if I can come up with an equation that will fit the graphs that we saw earlier, and then once I've got my equation, let me see if I can come up with a theory to explain that particular equation. So he started with this idea that, of course, that energy, which seems to be related to frequency, and we saw that as the temperature increases, that the frequencies shift to a higher frequency. So we start with this idea that energy is proportional to frequency, which we see here in this little equation, and nu, the Greek character nu, in this equation, of course, represents frequency. And so E equals n times h times nu shows that energy is proportional to frequency. N in this equation is a whole number, so it can take on values of 1 or 2 or 3 or 4, etc. And that h is what we call Planck's constant, and we'll come back to that in a few minutes. So the fact that n was a whole number seems to indicate that there are these packets of energy, and each packet has energy equal to h nu, and so when n is equal to 1, you have 1 packet, n is equal to 2, you have 2 packets, etc. So we've got this idea that we've got packets of light energy. Now let me point out at this point that Planck did not mean to imply that light itself always behaves this way. what Planck was suggesting is that when light interacts with matter, it transfers energy in these packets. And so this was more a function of the black body effect, but not an intrinsic property of light by itself. So here's the equation that Planck derived. It may seem a little foreign to you at this point, but this quantity on the left-hand side has this rho, this is the Greek character rho, as a function of frequency and temperature. That's what that means. So rho nu of t means that we have this function rho, which depends on frequency and temperature. And this function, we'll call it, this is the energy density. And we're multiplying it by d nu, okay? And you may recognize this, of course, from calculus. D nu here simply represents the infinitesimal quantity d nu. So an infinitesimal change in nu corresponds to d nu. And we'll come back to that in a few minutes. On the right-hand side, we have the expression itself for the energy density, and we will note, of course, that in this expression we have frequency in the numerator and frequency in the denominator. So we see two effects here. What this means is that if the term in the numerator would indicate that if frequency increases, that term increases, the entire term increases. But the function in the denominator would seem to indicate that as frequency increases, the spectral density decreases. So we get the spectral density decreasing from one term and increasing from the other. And of course, when you have a mathematical function which has two terms, one which shows an increase, the other shows a decrease, that's going to lead to a function which has a maximum at a particular, in this case, frequency. Again, h corresponds to Planck's constant. This is a constant that Planck discovered was necessary for his equations to work. The value is given here, and of course he didn't name it Planck's constant. It's since been named after him because it turns out to be a very, very important constant that we'll be using frequently through our discussion of quantum mechanics. Alright, so with this d nu here that corresponds to an infinitesimal change, how do we use this mathematically? What this means is if I want to determine the energy density over a region between two frequencies, nu 1 and nu 2, what I'm going to have to do is integrate. Our common answer for just about every mathematical manipulation we're going to have to do in PChem. If we want to find the answer, we have to integrate. So what we do is we take this Planck equation and plug it into an integral, and the limits of the integral correspond to the frequency range. When we do this integration, what we'll get is a number which represents the total energy density between those two frequencies. If we wanted to determine the total energy density overall, and again, this particular integral has the limits nu 1 and nu 2, but if we wanted to determine the total energy density, then what are we going to do? What would the limits be? Well, in that case, the limits would be, for total, 0 to infinity. That's how we would get the total energy density at a particular temperature. So we see from our discussion here that the only way to get an expression that accurately describes the black body phenomena requires that we use this concept that the energy of light is proportional to frequency. This, of course, was revolutionary. at the time, and it has some major implications for how we actually describe light. In this case, assuming that light behaves as a wave just doesn't give us the right results. All right, so let's move on. And the other effect that we talked about that seemed to indicate that light behaving as a wave was an inadequate description is the photoelectric effect. As mentioned earlier, this is a simple effect where what we do is we look at light incident on a metal surface, and then after that, noting the electrons ejected from the metal surface and monitoring the current, or in fact the kinetic energy of those electrons as a result of the photoelectric effect. This is the principle behind many photodetectors, for example photomultiplier tubes, where we actually are able to use light, measure the intensity of light by monitoring the electrical current generated in these systems. So we have this photoelectric effect, and so light strikes the surface and electrons leave it. So that in itself is not unusual. Waves do have energy, and any kind of wave that strikes a surface could impart energy to that surface and result in something like electrons being ejected. The problem arises when you start to look at the behavior of the electrons that are ejected. So in this plot here, we see that the kinetic energy of the electrons ejected from the surface is plotted versus frequency. And once again, if we take a look at this, we'll see that the kinetic energy of these ejected electrons increases as we increase the frequency. In fact, we see that it's linear here in this particular plot, that we have this relationship again between energy and frequency. The other thing that's important is that not only does the energy increase as we increase the frequency, there is a threshold frequency below which no electrons will be ejected. So if we have a frequency less than the minimum value here, then we'll see nothing. No electrons are ejected. But once we reach the threshold frequency, we'll find that the electrons are ejected, and that we also see that the kinetic energy of those electrons is in fact proportional, or not proportional, but linear with the frequency itself. And that's a very important effect. So both of these effects, the threshold frequency and the fact that frequency, the kinetic energy increases as the frequency increases, again, not something that can be explained by the classical theory of waves. The energy of a wave is dependent on its amplitude, not on its frequency. That's true of sound waves, it's true of water waves. The frequency is not related to the energy. We have that. The other thing to note is the intensity dependence of the ejected electrons. We'll see that the kinetic energy of these ejected electrons, as was noted here, depends on frequency, not on the intensity or, again, the amplitude of the wave. The amplitude, the intensity of a wave is actually related to the square of the amplitude of the wave. So that classically we might expect, if we increase the intensity or amplitude of the wave, that we'd see electrons being ejected with greater energy. We do not see that. What we see instead is, as we increase the intensity, while the kinetic energy doesn't increase, the number of electrons ejected increases. So that's another important result. Again, none of these can be explained by classical theory. So a new theory has to be developed. And here's where Einstein steps into the picture. In 1905, Einstein at the time was a patent clerk, and it was a phenomenal year for him because he wrote and published 4 papers that revolutionized physics. Most of you are no doubt aware of his developments in relativity theory, but he also wrote a paper on the photoelectric effect and developed a theory, and it's actually for this work that he was awarded the Nobel Prize. So what Einstein basically did was he said, okay, I know that Planck did this work which seemed to indicate that that the energy of light was proportional to frequency. So let's just say that light consists of packets of energy, or quanta, as he referred to them, and those packets of energy had a value proportional to frequency equal to h nu. We of course know these packets now as refer to them as photons, but that term actually wasn't coined until 1926 by none other than G.N. Lewis. He of, for example, Lewis dot structures that you learned about in general chemistry. All right, so again, Einstein took this idea and said, well, okay, if we've got these packets of energy that show that energy increases as the frequency increases, well, then maybe that explains why the kinetic energy of ejected electrons would increase as the frequency increases. So the idea is that we have these packets, or what we now call photons, striking the metal surface, and for each photon striking the surface, should it have adequate energy, then it would eject one electron. So that was the idea here. Now the light intensity issue, we noted that what happened was that when the intensity of light increased, while we didn't see an increase in the kinetic energy of the electrons ejected, what we did see is an increase in the number of electrons ejected. Well, that now makes sense, because the light intensity increases means that the number of photons increase, and if the number of photons increase, then the number of electrons ejected would increase. The threshold frequency observation is due to the fact that below the threshold frequency, the light has insufficient energy to overcome the binding forces of the electron to the metal atoms. So essentially, the minimum energy required to eject an electron would be the ionization energy. If the energy of the photon is less than the energy of less than the ionization energy, then it's not going to eject the electron. And of course, since the photon energy depends on the frequency, if the frequency is less than this threshold value, not enough energy is available to eject the electron, so nothing happens. So the threshold frequency represents the frequency, and the minimum energy necessary to eject the electron, it represents the ionization energy. If the energy of the photon is greater than the ionization energy, then any of that excess energy that goes into it would then become the kinetic energy of the electron. So we have this basic equation then that explains this. The kinetic energy of the electron, E sub k, in this equation, is equal to the photon energy, which is the total energy striking the metal surface, minus what we call the work function. This is the Greek character phi. So the work function, which is equal to the ionization energy. So if you take the total energy incident on the surface, you subtract from that the energy necessary to ionize the electron, then any energy left over becomes the kinetic energy of the electron, which is, of course, is 1/2 mv squared. This is the equation for which Einstein won the Nobel Prize, explains the photoelectric effect. Now, I will add that in 1969, a paper was published that actually, in a physics journal, that actually showed that one could explain this photoelectric effect without requiring the use of photons, so that we know now that that Einstein's equation, which worked well, were not necessary to explain the photoelectric effect. But nonetheless, we have now this concept of packets of energy and light behaving as packets of energy, which are proportional to the frequency of the light in this case. Alright, so what do we have here? What we have here are two effects for which we have no classical explanations that are inadequate: the blackbody radiation effect and the photoelectric effect. Both of these effects require that light behaves as a collection of particles with energy equal to h nu, or in terms of wavelength, hc over lambda, given that the frequency is equal to c over lambda. So what are we to do with this? We certainly have experimental evidence, interference effects, the double slit experiment, diffraction processes, which indicate that light behaves as a wave. But these two effects, blackbody radiation and photoelectric, seem to indicate that light behaves as a particle. So which is it? Is it a wave? Is it a particle? Is it both? How do we deal with this strangeness? Well, people began asking even more questions about this when it comes to an examination of the behavior of matter. And that's a subject that we will discuss in our next video.